This lecture is going to introduce the idea of using differential equations to solve growth and decay models in mathematics. But before we do that, we need to see a technique of solving a certain type of differential equation before we actually get into the model issues. So this technique is an introduction. We'll see in the next lecture, we'll see a much more expanded discussion, but separation of variables is a technique for solving a certain class of differential equations. And here's what that means, okay? Let's just look at a couple of examples here. Suppose we have a differential equation where the derivative y prime is equal to 2x over y. We haven't seen anything quite like this before. Now what we've seen, and of course what we want to do, and I didn't state that, is we need to solve this differential equation. So what we've seen in the past, or previously, is that we change y prime into derivative of y with respect to x, so that we can deal with each of those differentials separately. That is the dy and the dx. Now, what we've seen is that we want to get things involving y on one side and things involving x on the other. And so in this case, if we multiplied both sides by y and both sides by dx, we would see an equation that looked like y dy is equal to 2x dx. Now, at this stage, since each side just involves one single variable, we could find the integral of each side. And so we'd have the integral of y dy is equal to the integral of 2x dx. And as we find each of these integrals, we know that we have a constant of integration on either side. We'll combine those into a single constant of integration. So as we integrate y with respect to y, we get 1/2 y squared. Okay, and when we integrate 2x with respect to x, we get x squared plus a constant of integration. Now, I'm going to write this down a bit here. I'm anticipating something, and normally we would just put a c there. I'm going to put a c subscript 1 because I'm anticipating this next step that I'm going to make. And if we can, it would be nice to write this equation a little differently, the solution a little differently. It would be nice to get rid of that fraction 1/2. And so what I'm going to do is multiply on both sides of this equation by 2. And 2 times 1/2 y squared, of course, is just y squared. And on the right side, we would end up with 2x squared, and then plus 2 times this constant integration, this arbitrary constant. Now, of course, this is just a constant. And, you know, c sub 1 with some constant, we don't know what it is. 2 times c sub 1 is just some constant. We don't know what it is. So I'm going to rewrite a little bit more, and I'm going to subtract the 2x squared from both sides. So I'll have y squared minus 2x squared. And on the right side, rather than leave 2 times c sub 1, I'm just going to rewrite that as a arbitrary constant of integration. And so there would be our solution. It's the way we would like to write it normally. Okay, let's look at this. We'll look at another one or two. Let's look at this particular example. In this case, we have, and we're to solve this differential equation. Solve the differential equation. Derivative of y with respect to x is equal to x times the quantity 1 plus y. Okay. Well, as we normally would do with the idea of separation of variables is simply that we get all of the y expressions on one side and all of the x expressions on the other. So to do that in this case, we would need to multiply both sides by dx, but we'd also need to divide both sides by 1 plus y, or multiply by the reciprocal of 1 plus y, which is my preference. So when we multiply by the reciprocal of 1 plus y, that would be multiplying by 1 over 1 plus y. So on the left side, I'll have 1 over 1 plus y times dy. And then on the right side, I'll have x dx. And that looks not too unfamiliar. So we would integrate both sides. We have the integral, and see, we've separated the variables. That's the whole issue here. So now it's possible to find the corresponding integrals. So integrating on both sides. Now, let's look at this left-hand side. And the integral of 1 over 1 plus y, well, we could do that by substitution, couldn't we? Thinking of 1 plus y as being u, that would be 1 over u. But then du itself would be just dy. So this is really 1 over u du, and so that would simplify or integrate to the natural log of the absolute value of 1 plus y. We're going to need to come back and talk about this in just a moment, and we will. Is equal to, now on the left side, when we integrate x, we'll have 1/2 x squared plus a constant that probably is going to get changed as we go through our work. Now, this is something that'll be a little bit uncomfortable if it's the first time you've seen this. And so I'm going to come back and look at this natural log of the absolute value of 1 plus y. And now, what I want you to recall, okay, if we have, let me pause for just a moment. Okay, I apologize for that little break there. Of course, you didn't notice it. Let's move on from here, and I'll address what I'm going to address in a moment. So, what this tells us, let's remember. I'm just going to make a point over here. If we have the natural log of anything is equal to some expression or number or whatever, that tells us that, of course, the base e to the power n is equal to the argument a. That's what that tells us, doesn't it? In fact, we can write it in either fashion. So as we look down here, and here's the issue. This is not a very good equation. You know, I guess in some sense we've solved it, but this is we'd rather write this in terms without the natural log if we can. So this would tell us that then the absolute value of 1 plus y, since that's the argument, is equal to e to the power, and the power is the right side of this equation. So that's a 1/2 x squared plus a c subscript 1. Now, rules of exponents would allow us to rewrite, if you will, the right side as e to the power 1/2 x squared times e to the power c subscript 1. After all, when we're multiplying like bases, we would add together the exponents, so we see that those are equivalent. Now, the significance there is that this portion is really, e is a constant, and if we raise it to a power that's a constant, we just have another constant. So we could rewrite this as the absolute value of 1 plus y is equal to, we'll replace e to the c subscript 1 as just some constant times e to the power 1/2 x squared. Now, here's a bit of what I was talking about a moment ago. Here's something that we need to know or need to realize, that this absolute value we can actually get rid of in a strange way. In fact, I tell you what I'm going to do. What I'm going to do here is take this c that I've got here and call it c subscript 2, just for the purposes of this example. So e to the power c sub 1 is just some other arbitrary constant I'm calling c sub 2. Now, if the absolute value is equal to something, then that means what we're taking as the absolute value of, that is, the absolute value of 1 plus y is equal to this right side. That means 1 plus y itself is either the positive or the negative of that right side. So we can rewrite our equation in this fashion. Now, because of what we have going on here, c sub 2 is a constant. And in front of that constant, we have a positive and or a negative. And so this is telling us that the constant we have in front of this e to the power is just some positive arbitrary constant, or as far as that goes, it could be some negative arbitrary constant. Just the fact is, it's an arbitrary constant. And so that allows us to say, okay, rather than just say plus or minus some constant, it's just going to be some constant. We haven't decided whether it's positive or negative. It could be either one. So we're going to replace that plus or minus c sub 2 with just the arbitrary constant c. Now, once we've done that, of course, we can take this and solve for y. And as we do, we would have y, we'd subtract 1 on both sides, so we'd have y is equal to c times e to the power 1/2 x squared, and of course minus 1, not as part of the exponent. So there's the solution to this differential equation, which of course was much more involved. Well, I think maybe we'll look at one more. I don't know. Let me go to the next page and I'll decide what we're going to do. Okay, before we get started with the real examples, if you do, I want to do one more introductory idea. And let me state this problem because there's a couple of issues that I want to point out. The rate of change, of p with respect to time, or with respect to t, usually t means time, is proportional to the expression 10 minus t. Find p, or solve for p. Well, there's a couple of issues here that we have to be concerned about. And the first is the rate of change of p with respect to t. Now, whenever we say rate of change, well, that's what derivatives are all about. They're studying the rate of change. And sometimes that rate of change is with respect to time. Sometimes it's just rate of change with respect to some other variable. But whenever we see rate of change, we should think derivative. And so that very first line, the rate of change of p with respect to t, is really referring to, okay, this refers to the derivative of p with respect to t. That's the rate of change of p with respect to t. So that's something important for us to know when we're dealing with problems of this type. Now the next thing, so it tells us that this derivative of p with respect to t is proportional to something. Well, now, to say one item is proportional to another means the items are related by a constant factor. That is to say, x is proportional to y means that x is equal to some constant times y. And sometimes that we don't know what that constant is. So that's what we mean by proportional. And that constant we call the constant of proportionality, or sometimes just the proportionality constant. Okay, so anyway, what this tells us then, because of the proportionality here, what we're given, basically, we're given that the derivative of p, that's the rate of change of p with respect to t, is equal to some k, some constant, times 10 minus t. So that k is called the constant of proportionality. Okay? Well, once we have that, of course, we've got a differential equation, don't we? So to find p, which is what we're asked to do, we need to solve the differential equation that we see here. Derivative of p with respect to t is equal to k times 10 minus t. Now, k is a constant. P and t are the variables. So as we go about this, of course, we're going to do something similar to what we've done previously. We're going to multiply both sides, in this case, by dt. So we'll have dp is equal to k times 10 minus t times dt. And in this particular case, as you see, we don't have any p's except associated with the differential dp. So we don't need to get p's to the left side. The right side involves a constant and t's. So that's all we need to be concerned about here. Okay, well, then as we proceed here, then we would take the integral of both sides. So we'd have the integral of dp is equal to the integral of k times 10 minus t dt. Now, of course, we understand from the integral of dp to be just p. We understand that. And on the right side, of course, we've got this constant of proportionality, but it's a factor that's a constant, so we can factor it out. And so our left side changes to something that looks a little easier for us to deal with. Now, of course, in this case, the integral of 10 with respect to, here we go, the integral of 10 with respect to t would just be 10t, minus the integral of t with respect to t is just 1/2 t squared. And of course, we've got this constant integration that we know that is on both sides, but we gather them all to one side. And then we could clearly write p as 10 kt, that is, we'll distribute that k, minus 1/2 k t squared plus a constant of integration. But we could have done this a little bit differently and found a little different look to our answer. But I think in this case that's good enough. That's good enough. So on the next page, we'll get started with actually the mathematical models. That's the growth and decay models that we're actually going to be working with to solve some word problems. Okay, finally, we're going to look at population growth. Let me just give you a little background. One of the earliest attempts to model human population growth was done by an economist, an English economist, Thomas Malthus. I think he lived in the late 1700s to early 1800s. And his model assumes that the rate at which a population of a country grows or increases is proportional to the total population of the country at that particular given time. In other words, the more people there are at some time t, the more there are going to be in the future, because the growth rate is increasing. So in mathematical terms, let's write this down mathematically, and this is really the big deal up here is the assumption is the rate at which the population grows. Well, of course, rate again is something we recognize as a derivative. So what this is assuming mathematically, or writing this mathematically, if you will, is that the rate of change of the population with respect to time is proportional to the particular population at a given time. So that means it has to be equal to the population via some factor, constant factor, k. So this side, of course, represents the rate of growth. And of course, this is the constant of proportionality, this k. And of course, this P is, capital P, is the population at time t. And of course, that's the variable. The only constant here is the constant of proportionality. The rate of change is growing, the rate of growth is changing, and the population is changing. Now, of course, there's some issues here that we just, let's see where this leads us, I guess. But what we should recognize is that there's a lot of things that aren't really considered here. In this particular setting, this doesn't take into account factors like immigration or other things that can influence the way populations grow. So this is a pretty simplistic idea, but it is important for us to understand the idea. Anyway, we can solve that differential equation. And so what we're going to do is we're going to separate the variables. Now we see that we have dp on the left side and p on the right side. And so to go about solving this, we would multiply both sides by 1 over p, and we'd multiply both sides by dt. And so we get something that looks like this. Now, here, when we go about taking the integral on both sides, we'd have the integral of 1 over p dp is equal to the integral of k dt. Now, on the right side, the integral of 1 over p with respect to p would be the natural log of p, absolute value of p. And on the right side, we would just have kt, wouldn't we? K times t, plus our constant of proportion, our constant of integration, which I'm going to label as c sub 1. Now, one thing we should think about here, we could go to a lot of work, but we do know that we can't have a negative population, so we do know that p is actually greater than 0, so it would be easy for us to rewrite this in this particular case as just the natural log of p is equal to kt plus c sub 1. Now we can go back to the idea of, well, for the natural log of p to be equal to something, that means what we're taking the natural log of is e to the power that's what the natural log is equal to, and as we saw a moment ago. So this is really just p is equal to e to the power kt plus c sub 1. And then we saw that we could break that into e to two different powers, and one of the powers would be e to the c subscript 1, which we'll just write as a power itself. So here's what we're really doing. We're going to replace, let me write it down here. The c, remember, ended up being e to the power c sub 1. C sub 1 is a constant, so e to that power is a constant. And so rather than make that ugly constant there, we're just going to write it as a capital C. Now, as I introduced this is really thinking about the population growth of human beings in a country. But this population growth can be for all types of populations. It doesn't have to be people. It might be bacteria. In fact, we'll see that here in a quick example here in a moment. But there's so we really call this the growth decay model. That's really what this is called, the growth decay model. And you know, in the college algebra or pre-calculus, you were given this model or some form of this model, but it wasn't really explained where it came from. Well, you see that it's a solution to this type of differential equation. And so we came about it in a very natural way. Now, There's a couple of things that I'd like you to know, and one is this capital C is the initial value. What does that mean? Is the value of P in this case, it's the value of P when T is 0, the initial value. Well, obviously, see, if T is equal to 0, then P, okay, will equal P will equal to C times e to the power k times 0. But k times 0 is just 0, and so this ends up being P is equal to C. In other words, at time 0, the population is C. So C stands for the population and I should have said here the initial value of P, but we'll see this again in a moment if it's not clear now. K is a proportionality constant, We've already talked about that, but let's just making a point of it. Now, and of course, T is time, and it can be measured in different ways. We might be measuring it in seconds, minutes, days, years, or some other measurement. It is important also to recognize here, and we'll talk about this in a little greater detail, that here we're talking about population growth, the way we introduced this. But this is, as I said above, it's both the growth and decay model. If K is 0, is positive, greater than 0, then we have a growth model. That is, the population is getting larger, or the amount of whatever we're measuring is getting larger. So this is a growth model in that case. In the case that K is a negative number, then we would actually have a decay model. Just kind of keep that in mind as we go through these examples. Okay, well, let's, on the next page, I'm actually going to have a problem for us to work on. So let me pause and we'll go there. Okay, as mentioned, this is a sample about the growth of bacteria. A freshly inoculated culture of Streptococcus pei bacteria, yes, that is strep throat, contains 100 cells. 60 minutes later, it is checked and has 450 cells present. 60 minutes later, okay. Assuming exponential growth, determine the number of cells present at any given time in minutes and find the doubling time. That is, from any given time, how long it takes for that population to double. Now, the first issue is assuming exponential growth. And that really is a matter of what we've already discussed, but let me just kind of remind you whenever we see that. Let's assume that we're going to have some variable, and it doesn't matter what we call it. It could be A for amount, it could be P for population. I'm just calling it Y. That is, Y is the amount, the number of cells present at time t. And we might refer to that as y of t also, of course. And so in this case, y prime is the rate of change. So, excuse me, the rate of change of y with respect to t. With respect to t. Now, what that boils down to, okay, let's kind of, so that whenever we see exponential growth, that means the rate of change is proportional, that is, to the amount at time t. That's what we mean by exponential growth. And so in general, what we saw that would relate to or change to as the derivative of y with respect to t is k times y. And of course we took that further and we solved that differential equation, or one that looks similar to it, by separating the variables. Okay, we've already done this, I recognize, but I'm trying to relate it to the kind of problems we see in general. We just need to be able to deal with these. And so that would mean, whoops, the integral of the left side is the natural log of y, absolute value of y, and the integral of the right side is kt plus a constant. And then because we're talking about an amount present, we could never have a negative amount present. I suppose we could have 0, but we're really not expecting that. So we're going to assume y is positive, and so we could just say that's the natural log of y rather than absolute value. And then by the definition of logarithms, that would mean y is equal to e to the power kt plus c sub 1. And we've seen already that we could write that as some other constant times e to the power kt. And so it boils down to, whenever we see exponential growth, this is the model. See, that's what it tells us when we have exponential growth. That's our model. Now, here's what we have to do in this problem, is that this is what our model looks like, but there's two unknowns, see, there for us right now. We don't know what this C is, see, or maybe we do. I should say our model is incomplete, and we don't know what this K is. So that's an unknown. And for our model to be complete, we need to know those values. And once we know those values, then we can calculate y, the amount present, for any t that we put into the formula. So to complete the formula, or the model, we need to know c and k. Now, c is, remember, is the initial amount. So we ought to be able to say c is equal to 0. But we could do it this way. So when t is 0, then that's at the initial time, then we know the amount is 100. Whoops, 100. And so our model would look like y is equal to c times e to the power k times our t value of 0. And we did this a while ago. And of course, on the right side, we have c times e to the 0 power, and e to the 0 is 1. And so we end up with 100 is equal to c, or c is equal to 100. So these pieces tell us a little bit more about our model. Now we know, because of that information, the initial amount, c, we knew it. We could have done this directly once we completely understand. So now the only thing we need to know before we can finish the first part of this problem is what the value of k is. Well, the other information helps us there, because we're told that after 60 minutes, we could say after 1 hour, but remember we're supposed to do these things in terms of minutes, so we want to measure t in minutes. After 60 minutes, time of 60 minutes, the amount present is 450, so y is 450. Well, if we put those values into this model, so we'd put a 450 for our y. Of course, we know now 100 is in front, e to a power k, which we don't know, but in this piece, we know that the t value is 60. And so we can go and solve the equation that we have here to figure out the value of k. That's the only unknown in this. And how do we do that? Well, we could divide on both sides by 100, couldn't we? And 450 divided by 100 is 4.5. So we'd have 4.5 is equal to e to the power, we'll say 60k instead of k times 60. And now we could take we should know how to do this, take the logarithm of both sides, of course, so the logarithm of 4.5 is equal to the logarithm of e to the 60k power, the power 60k. But the logarithm of e to a power is just the power, so that's equal to 60 times k. And so then we can easily solve for k and say, oh, okay, k is equal to the natural logarithm of 4.5, whatever that decimal number is, divided by 60. Now, we can get our calculator out and approximate that, and that's approximately equal to 0.02507. And I've gone several decimal points, as you can see. Now, using this information, our model is complete. So as I go to the next page, when I say our model is complete, we ought to be able to, let me see where I've got my answers here, just a moment here. Okay, I'm sorry for pausing on you. So what was the original, the original question? Determine the number of cells present at any time t. Well, that part really says find the model, doesn't it? Find the complete model. It didn't tell us particularly how many minutes we wanted to do this for, so our model then, with that information, our model we could write as y is equal to 100 times e to a power of k times t. But we found the k is approximately equal to, we could put the natural log of 4.5 over 60, but we'll just use the approximated value of k, so 0.02507 t. So with this formula, for any amount of minutes t, all we need to put in is that value t, and we'll know the population or the number of cells of bacteria at that time. So we've done the first part. On this next page, we'll do the second part, and that is find the doubling time. So let me pause and we'll go to the next page. I've rewritten our model, and we're asked for the doubling time, which means what's the amount of time it takes for the population to double. So there's some real question here about what that means, because are we talking about the population from 100 or from 450 or from any other time? Now, we can certainly see how long it takes the population to double from 100, okay? Double from 100. Okay, so well, what we would do is that would imply our time is when that we're looking for is when y is actually 200, isn't it? We want to know the time when the population is double, and of course that means y is 200. So we could go through here and we could easily put these pieces together, and we could say, okay, our y value is 200. It's the time that we don't know, and so we have our model, or our equation, if you will. Whoops. Sometimes I have a hard time speaking and writing at the same time. Okay, so that's what we need to solve, so we divide on both sides by 100, and we would end up with this. And then we take the natural log of both sides. Of course, 200 divided by 100 is just 2, isn't it? And we take the natural log of this right side as well, but the natural log of e to a power is just the power. So we end up with the natural log of 2 is equal to 0.02507 t. And so t itself would be at least approximately, well, t itself is equal to exactly the natural log of 2 divided by, I guess not exactly, because this decimal was approximation to begin with, wasn't it? But if I put my calculator to that, in fact, let me do that. Let me put my calculator to it. Let me pause for a moment. As I put my calculator to that, I get approximately 27.65 minutes. Remember, we're measuring in minutes. So a little more than 27.5 minutes is how long it takes to double. Now, this is kind of something that I want to point out that's interesting here. It said find the doubling time, and we made an assumption that it meant from doubling from 100 to 200, doubling that 100 that we started with. But what's interesting is that for a growth model, an exponential growth model, the doubling time is the same no matter from where to, if you start with 450 cells, to double that to get to 900 is going to take 27.65 minutes. Or if you've let the culture grow for a while and now you have 1,000 cells and you want to know how long it's going to take before that's going to be 2,000 cells, well, that's going to be 27.65 minutes. No matter from where you start, it will take 27.65 minutes to double the population that you're starting from, regardless of when the time is. Now, the main thing to recognize is that the K value, that's K, that's 0.02507, okay, that is a constant for this model in general. That is, for this bacteria, okay? For this bacteria, that is a constant. And so if we started with, let's just say we start with, whoops, don't need with twice, do we? We start with a population of C. That's the number we're going to start with, cells. Okay. K is still 0.02507. Because that's the nature of this bacteria. Okay, so that part's not changing. Well, then if we start with C, to double the amount. Now, see, we may be starting with C further out. That is, the growth has been there for a while. But now we have a population of C. Okay, so in that case, to double it, the Y we're talking about is 2C because we're doubling what we start with. But we would still, so this is what we're starting with, and this is double. So start with, and this is double that. And we want to know how long it takes to double it. But E still has the power 0.02507 T on it. And so that's what our equation would look like. And so when we divide on both sides by this constant C that's on the right side, we would have something that looks like this. And of course, when we simplify the left side, that's just a 2. And then when we take the logarithm of both sides, oh, this looks very familiar, doesn't it? In fact, this is exactly what we had right up here, isn't it? It's exactly what we had. And so we'll go through a few more steps, but we'll find out that T is still 27.65 minutes. So it doesn't matter what we're doubling from, it's going to take 27.65 minutes. Okay, well, we're ready for a new example. This is about radioactive decay. So I'll start that on the next page. We shift our talk from growth to decay, and specifically right now radioactive decay. Let me just let me read to you a bit. I apologize for that, but it's kind of important to understand a little bit before we get started with the problem. The nucleus of an atom consists of combinations of protons and neutrons. Many times these particular combinations of protons and neutrons are unstable. That is, that the atoms decay or transmute into atoms of another substance. Such atoms are said to be radioactive. So the idea, usually we think about radioactive as it decays, it disappears, that the substance disappears. Well, yes, the original substance is not there any longer, but it doesn't mean that the mass is not there. It changes to something else. So that's really what we mean. It doesn't disappear, it changes. For example, over time, the highly radioactive radium, radium-226, transmutes into the radioactive gas radon, which is radium-222. So that's just one particular example. Of course, uranium decays into or transmutes into lead. So, there's all kinds of things, all types of different things that we don't understand. I mean, we as math students don't know a lot about, but that's what you study in physics quite a bit. Anyway, to model the phenomena of radioactive decay, it is assumed that the rate of decay, that's the rate of change of the amount with time. So the rate of decay, and that's what this is, the rate of decay, of the nucleus of a substance is proportional to the amount of the substance remaining at time t. And so, what that means, of course, that is to say that mathematically, that is that the derivative of A with respect to t is k times A, where k is a proportionality constant. And of course, this is very similar to what we saw earlier. This leads to the equation A is equal to some constant times e to the power kt. Looks almost identical. In fact, the only difference here really is the letter that I used. In this case, I used an A as opposed to a Y previously. Now, so once again, and sometimes we might replace A with A sub t. But in this particular case, when we're talking about K, this K is going to be less than 0 because we're talking about decay. And it's called the decay constant. Of course, that was that proportionality constant before. Earlier, when we have a growth situation, the K is called a growth constant, and the K is greater than 0. And these really relate to two different graphs that we're used to. We know what the normal exponential graph looks like. I'll just put it this way, okay, because we're usually talking about time. See, this would be the time axis, and this would be the amount axis, okay? And so as time progresses, then we're growing in this case. So this is where k is greater than 0, okay? And on the other hand, when k is less than 0, we have something that looks like this. That's the exponential function. This would be when k is less than 0. So this is a growth look, and this is the decay look. It's the same, basically the same type of equation or the same type of model. Now, something else this model we're going to get used to. And another way this is written, by the way, like I said, we might replace A with A of t, meaning A, the amount, is a function of time. And many times we make the initial amount, the C, will replace with an A subscript 0. And a lot of times we pronounce that or call that A naught. Okay, so that's the initial amount or starting amount. Whoops. Okay, and so another way to write the same thing. Or we could, another way to write the same thing. Now, also in radioactive decay, we'll hear another term that is half-life. Okay, we'll hear that a lot. And half-life is simply the amount of time it takes a substance to decay by half. In other words, if the half-life was 500 years of a substance, then if we started out with 10 grams, then in 500 years we would have only 5 grams. And then in another 500 years we would have 2.5 grams. So the half-life measures how long it takes for half of the substance to decay at any given time. Well, on the next page, we'll actually work on a particular problem. So let me pause here and we'll get started there. Okay, you can see in our example here, our problem, radioactive radium has a half-life of about 1,620 years. What percent of a given amount remains after 100 years? So this is not an idea of what given amount. Regardless of the amount we're given, what percent of that amount will remain after 100 years? Now, we're going to assume the exponential decay model. That is, we're going to assume this is modeled by A is equal to A naught E times e to the power k times t. And just as before, there's several pieces of information that we need. But let me, we need to decide somewhere along the way. Now, we don't really know how much we're starting with here, do we? We don't know that amount. That's not told to us. But what we're going to find out as we work through this problem is the amount we start with doesn't have anything to do with what percentage we'll have left after 100 years, because this decays at the same rate all the time. The next thing that we need to recognize or deal with is that the half-life will determine, if you will, and it in fact has something to do with the decay rate. Half-life will determine K, of course, which is the decay rate. It doesn't tell us directly. And so here's the way we go about thinking this through. Regardless of, okay, so for half-life is T, in this case, 1,620 years. So when T is 620 years, if we start with any particular amount, if we start with, say, amount a sub 0, then after 1,620 years, the amount left, the amount A, will be equal to 1/2 of what we started with. Okay, that's the big issue here. So that means when T is 1620, A is 1/2 of A naught. So we'd have 1/2 of A naught is equal to A naught times e to the power k times, but this is specifically true when T is 1620. That's a whole deal with half-life. Now, what we need to do is solve for K. Okay, that's what we're after. We need to solve for K. And when we solve for K, then we'll be able to determine things, we'll know what the model really looks like, or at least we'll be closer to the model. So solving for K, we need to divide both sides by A sub 0, A naught. We'll have the left side, 1/2 A naught, divided by A naught, is equal to e to the power, k times 1620 is 1620k, isn't it? Now, of course, on the left side, the A naughts will cancel, and we'll be left with 1/2 is equal to e to the power 1620 times k. And when we take the natural log of both sides to find k, this is what it would look like. But of course, we know the natural log of e to the power is just the power. So we would have on the right side 1620k, and on, of course, the left side natural log of 1/2. And so when we divide on both sides by 1620, we'll have the k value. So that is, k is the natural log of the number 1/2 divided by, after we calculate natural log, 1620. So in this case, we can approximate that. In fact, I have, okay, and my approximation is negative 0.000042787. Now, more generally, and notice this, that the only thing that was something given to us was the particular half-life. I mean, that what I mean is regardless of the model, if we were putting in half-life information, we start with a sub naught. After the half-life years, we would end up with 1/2 a sub naught. And so it's the half-life itself that makes a difference. So more generally, we might recognize that the decay rate, the K value, is always going to, when we're talking about radioactive decay, is always going to be the natural log of 1/2 divided by the half-life. That's exactly what happened here. So we might do that more quickly in the future. Now, here's the situation that we have. We know for our particular model now that it's going to be A is equal to A naught times e to a power k times t. Oh, by the way, notice our k is negative, and that's what we were saying earlier, that the decay rate, the k value, will show up as a negative in the model. So here it's negative 0.004287. That's our k value, but it's k times t is the exponent, isn't it? So now, anytime we know an initial amount A naught, we'll have the completed model, and we can calculate the amount of radium at any given left at any given time in years. Now, our problem though says what percent of a given amount remains after 100 years. So specifically for us, what is the percent? Is the percent, the percent of A naught present after 100 years. Okay, and of course that's a t value, isn't it? So what we would end up doing is we would calculate the amount left after 100 years, and that would be the amount first, not the percent. So that would be, now we don't know what we're starting with, but that doesn't matter. It would be the amount we start with times e to the power negative 0.00, actually I left a zero out down here, didn't I? I apologize. There's an extra zero that I didn't put in there. 0.0004287, but our t value is 100 years. And so we have A is equal to A naught times e to the power, that is, I probably shouldn't be writing all this extra detail down. It's going to be negative 0.04287 after we multiply with 100. And that's going to tell us then that it's A naught times, when I calculate that with my calculator, that's about 0.958. That's what that is. Okay, so that tells us if we start with C, we have a 0.95. If we start, with A sub naught, we have 0.958 times that amount left. In other words, we will have 95.8% that remains after 100 years. And of course that comes from converting this decimal into a percentage. Okay, on the next page, I'd like to continue this talk about radioactive decay and how it's used in dating fossils, and that's called carbon dating. So we'll do that on the next page. And you can see this example, or this problem. A fossilized bone is found, and it's found to contain only 1/1000th of the original amount of carbon-14 as when the animal died. Determine the age of the fossil. Now, let me give you a little bit of background before we work on this problem, and hopefully that will help. I guess it was in the 1940s, a chemist by the name of Willard Libby devised a method for using radioactive carbon, that's carbon-14, to approximate the age of fossils. And it's basically, it's based on this idea that the amount of, the ratio of the amount of carbon-14 to the amount of ordinary carbon in the atmosphere appears to be constant over years and years and years. And the amount of carbon-14 in living tissue, whether it be bones, whether it be hair, whether it be trees, is the same as in living tissue is the same as that in the atmosphere, because through breathing, through water, through osmosis, that carbon-14 is becomes part of the living tissue. But once that animal dies or that tree dies, then carbon-14 is no longer coming into that tissue. And carbon-14, of course, decays because it's radioactive. And so it starts decaying, and so later on there's not as much carbon-14 in that fossil, for instance, as there was when it died, as there is in the atmosphere now. And what's in the atmosphere now is a constant, at least based on the amount of carbon in the atmosphere. So that's what this whole thing is based on. And of course it has, in fact, Libby got a Nobel Prize in 1960 for his work here, because it's helped date Egyptian tombs and Dead Sea Scrolls and even the controversial Shroud of Turin. So all kinds of things. I mean, certainly fossils. So let's get started with the problem. Sorry to go on and on about this. The starting point is that we're assuming radioactive decay, and so we're going to assume or start with a model. The amount A of t is equal to A sub naught times e to the power kt. And of course k is, once again, the decay constant, okay? And we saw earlier we could go through a process to figure out what k is, but we found out going through that process on the previous example, by using the half-life, we can simply calculate that k ends up being the natural log of 1/2, divided by the half-life of 5,730 years. And you can look at the previous example to see how we did that. Okay, but and in this case, that's approximately, and it's negative again, 0.000120097. Okay. Now, given that information, then we know our model, okay, for the amount of carbon-14 decay, based on the decay of carbon-14, is given by A naught times e to the power negative 0.000120097 t. So we ought to be able to calculate the amount we have left of carbon-14 if we know the amount that we're starting with. But in this problem, okay, so how does that apply here? Because we're supposed to determine the age of this fossil, so we need to find a time. But what we have here is we need to find the value of t. Okay, we need to find the value of t where, where a of t is 1/1000th of A naught. Remember, there's so much carbon 14 in the living substance, in the living animal, and we've found out that there's only 1/1000th of the original amount, although we don't necessarily need to know the original amount. So we're wanting to know when A sub t is 1/1000th of the original amount. So we end up with an equation that looks like 1/1000th of A naught, that's the A of t amount, what we're looking for, that we're expecting to have, is equal to A naught times e to the power negative 0.000120097 t. Now, we need to solve for t. That's what we're trying to do all along, solve for t. Determine, so t will be the number of years passed since the death of the animal that will give us 1/1000th of the original amount of carbon 14. We divide on both sides by A sub naught, and when we do, we'll end up with, 1/1000th is equal to e to this ugly power. Okay. When we take the logarithm of both sides, we'll have the natural log of 1/1000th is equal to negative 0.000120097 t, and so t will be the natural log of that 1/1000th divided by this negative ugly decimal, 0.097. And as I calculate, I get approximately 57,103. And remember, that's measured in years. Well, that's pretty cool, isn't it? Well, in this particular example, we're kind of on the edge of how the accuracy of carbon dating. That's what this is called, is carbon dating. And we find out for reasons based on physics and chemistry that around 50,000 years is about as accurate as we can get doing carbon dating. There are other methods for things that are older than that, so we're kind of on the cusp here. But it's still the way we would approach a problem like this in general. Well, in the next problem, we're going to change from this type of decay, going to deal with Newton's law of cooling and how we can use differential equations and modeling to solve problems dealing with Newton's law of cooling. So we'll look at that. Before we do the first problem dealing with Newton's law of cooling, we need to know what it is. So as I read it to you, the rate of change, Newton's law of cooling says that the rate of change in temperature of an object is proportional to the difference between the object's temperature and that of the surrounding medium, like the room temperature, for instance. Now, in calculus, what this says is the derivative of temperature with respect to time. So capital T is temperature, lowercase t is time. So that's the rate of change of the temperature. And it says that it's proportional, so that means there's a constant proportionality to the difference between the temperature of the object, okay, the temperature of the object, and the temperature of the medium that the object is in. So that's the temperature of the surroundings. Now, this temperature is a constant. That's the temperature surroundings. The temperature of the object is the variable. That's what's changing. Okay, and of course, this is the constant of proportionality, so that's a constant. So that's Newton's law of cooling, written in calculus terms. Let me write down the problem we're going to work on. Let me pause, and then I'll come right back. Okay. A cup of fast food coffee is 180 degrees when served. After 2 minutes in a room of 70 degrees, the coffee has cooled to 165 degrees. What will be the temperature of the coffee 5 minutes after being served? Okay. Now, here we'll start with Newton's law of cooling. Okay, and that is that the derivative of the temperature with respect to time is some k, some constant, times the difference of the temperature of the coffee, in this case, we're calling that T, that's the variable, minus the temperature of the surroundings, well, the surrounding medium. In this case, surrounding medium is the air in the room, and it's at 70 degrees. So for this particular problem, that's what our differential equation looks like. Now we need to solve that differential equation, because what we need is a formula for T. We need to know what the function T is, and once we know that is the function T being the temperature of the coffee based on any given time. And if we come up with that, all we need to do is put 5 minutes in for T, and we'll be able to calculate the temperature. So we start out by solving this differential equation, and we do it with a matter of separation of the variables. Because capital T is on the right side, we're going to multiply by dt on both sides and divide by t minus 70 on both, capital T minus 70. So it's going to look like this: 1 over t minus 70 times d capital T is k times d lowercase t. Now, when we go about taking the integral of both sides, on this left side, we'll end up with the natural log of absolute value of t minus 70 is equal to kt plus a constant of integration. Now, the coffee is cooling, but it's never going to be cooler than the room temperature. So T minus 70 is positive, isn't it? So we could actually just write this as the natural log of T minus 70, and we don't really have any use for those absolute values in this case. Remember, that's because we know T minus 70 has to be positive. The temperature can't be, the temperature of the coffee can't be less than the room temperature. Now, this is going to lead to, we've seen this before. This is going to lead to T minus 70 is equal to e to the power kt plus c. But we've seen this before. That's going to be T minus 70 is equal to e to the c times e to the kt. And e to the c we're just going to write as some arbitrary constant k. Some arbitrary constant c times e to the kt. So we've been through this several times already. And so now we're going to solve for t by adding 70 to both sides. Now, what do we know? Okay, see, we don't really have a full model yet, because we don't know c and we don't know 70. And in this case, c is not, this isn't like what we've had before when we had exponential growth and decay. In this case, the c is not the initial temperature. Okay, so we have to approach this a little differently. But here's what we have. We know that when, at the time of serving, that's when time is 0, then we have the temperature T is 180 degrees, capital T. So we can use that information in this partial model below. For capital T, we put in 180. Then we have C, which we don't know, times e to a power k times 0. See, our lowercase t is 0, plus 70. So k times 0 is 0, e to the 0 is 1, so this becomes 180 is equal to c plus 70. And so we solve for c and get that it's 180 minus 70, or 110. So now we know that our model looks like this. Temperature T is equal to 110 times e to the kt plus 70. But we still don't know k. And for us to have a complete model, we've got to find k. Okay, well, we have more information. We know that when t is 2 minutes, then capital T, the temperature is 165 degrees. And I'm betting that information will help us calculate what k is. So we'll do that on the next page. Because like I said, we're at the model. I've written the model from as far as we know. And then we further know that when the time is 2, when lowercase t is 2, the temperature of the coffee, uppercase T, is 165. And so that allows us to solve for k. 165 for the temperature is equal to 110 times e to a power that is the unknown k, but a time of 2 plus 70. So we'll go through the steps, and I'm convinced that you can do those steps. That will lead us to k. Well, maybe I ought to do this. I apologize. Let me come back here. What we'll do is subtract 70 on both sides, and so we'll end up with 95 is equal to 100 times e to the power 2k. And then we're solving for k, so we need to get the e to the 2k alone. So we'll divide on both sides by 100, and then we'll have this. And then we'll take the natural log of both sides. But of course, the natural log of e to the power is just the power. So we end up with the natural log of 95 divided by 100 is equal to 2k. So k itself, what we're looking for, is the natural log of 95 over 100, and the natural log is divided by 2. And using my calculator, I get that to be approximately negative 0.073302. So finally, we have the model. All that was to just come up with the formula or the model. We have the model. We know all the components of the model. And that is the temperature T is equal to 110 times e to a power k times t, but we're lowercase t, which is at the time. So it's negative 0.073302 t, lowercase t, and then not part of the exponent, remember, is our plus 70. So after 5 minutes, of serving, that's when lowercase t is 5, then we can calculate the temperature of the coffee. The temperature of the coffee is given by T is equal to 110 times e to the power negative 0.073302 The time is 5 plus a 70, and it's just a calculator exercise then, and that comes up to be approximately 146. And of course, we're talking about degrees here. So after 5 minutes, the coffee will still be 146 degrees. Well, I think that does it for this section and this lecture. I hope that you find this useful when you're working on your homework. Signing off.